A Hilbert space by itself is a place where nothing ever happens. So what's a Hilbert space? A Hilbert space is a vector space. It's an abstract mathematical object. And if you think of a system as having what physicists call degrees of freedom, which means characteristics that can vary in some way or other, then you take all the degrees of freedom and you take all the ways that they can vary, and every single distinct possible configuration of degrees of freedom having values, you assign a vector to.
Okay.
And you put all of those vectors into a big abstract space with enormous dimensionality.
Right.
And that's a Hilbert space. And so if you want to say, what's the state of the entire system, then it's some vector in that space, because that's the way you've defined the space. It's the space of all possibilities. And if you think of what's that system doing, it's just exploring the possibilities in its space of possibilities. So its state is some vector that's migrating around in that space of possibilities. And that migration process has a description in quantum theory, which is called unitary evolution. And what that means is no information is lost in this evolution.
So
no information is gained either.
It's sort of like a clockwork, deterministic.
Yeah, it's actually very much like the concept of Laplace, when everything affected everything else instantaneously.
Right. So there are no probabilities involved. What's going to happen from a instance to instance is completely determined by the previous state.
It's determined by the evolution itself. And this whole picture becomes intuitively, it's very difficult to keep in your mind, because when we think of a system evolving, we think of it as evolving in time, but there's no clock. There's no external clock. There's just this universe. So if there are any clocks, the clocks are on the inside, and their states are part of the migration of the state vector.
Interesting.
So we can't really bring these intuitions about time into thinking about a universe using quantum theory.
Got it. So what you were saying was there is no information to be gained because no information is lost. So there's no uncertainty. And when we talk about observation, which is always about uncertainty reduction, then the reason it's classical is because at the whole universe scale, there is no observation to be made.
Right. Yeah. To talk about observation, you have to cut the universe in two.
Okay. And again, what did you mean when you said this information exists at a boundary?
So if you think of, you've got your universe, right? You slice it in two. So you've got the left half, call it A, and the right half, call it B, and they're interacting. And so you can ask, how big is this interaction compared to the sizes of A and B? Well, remember, previously we were talking about this assumption that we have to make that the interaction is weak.
Yeah.
In order for A and B to have well-defined states. So if the interaction is weak, it means that the area, if you will, there's no space-time here yet, right? The The area, if you will, where the interaction is taking place is kind of small with respect to the whole degrees of freedom of A and B.
Okay.
They're just interacting a little bit. So you can think of that interaction, and here we'll actually think about little spinning things, right? That interaction has a particular dimensionality, which is given by how many degrees of freedom are involved in actually interacting.
Right.
How many degrees of freedom are touching each other, if you will. And that dimensionality can be represented mathematically when we write down the interaction. And one can always represent that interaction mathematically by assuming that what the systems are doing is exchanging bits. And if you want to think of it, you can imagine that they have a whole string of quantum bits, of little spins. And what the system A does is arrange those spins in some particular pattern, up, down, up, down, up, down, up, down. And system A has her own idea of what up means and what down means. And then system B over here looks at those spins and makes measurements. So and system B has its own idea of what up is and what down is. A and B are different, so they can have completely different ideas. So if A says, okay, spin number one is up this way, but up for B is this way.
Right. Then
when B, using this direction for up, measures this spin, it's perpendicular. So its probabilities are going to be the same, one way or the other. But if B happens to think that up is this way, then it will get the value 1 all the time.
Right.
So you can think of these systems as exchanging bits, but with an uncertainty. The uncertainty is based on their possible disagreement about what they mean by up.
Right. Yeah. I mean, the uncertainty is in lack of shared vocabulary or
right.
incomplete overlap.
Yeah. And you've cut the system in two. This is their only communication, is arranging these bits.
Right.
So there's no prior agreement about what counts as up. So the holographic principle is just the idea that we can always represent this kind of encoding of information as encoded on a surface at a particular scale. And that principle comes from black hole physics and as a way of talking about how much information can be obtained from a black hole by someone looking at it from the outside. And it's exactly proportional to the surface area, not to the volume. Hence the idea of holography. But it's also clear if you just think about it in this more abstract way of two systems exchanging information. We've made the assumption that, that the interaction is weak. So the systems don't know much about each other. They just know what's encodable on this shared sequence of bits or shared little holographic screen that they're writing bits on.
Right. I mean, it sort of reminds me of how, say, something like cryptography works, where there is this exchange of information, but through a channel, and you have to define the protocol first. Otherwise, nothing makes sense.
Right. Exactly. I mean, it applies to any communication set.
Right. Right. So, Dr. Field, since, we are coming to the end of our conversation, I wanted to sort of just explore as a last bit, how does this all connect to panpsychism, I know in one of the talks you mentioned that you feel it's inevitable feature. I mean, panpsychism is where consciousness or this experience is a feature of the universe. So can you talk about how did you arrive at that view, if I'm capturing it correctly?
I would say that if one thinks about observation and measurement in this way that we've just been describing, then that description is completely independent of what the systems we're talking about are. It's completely independent of how we've sliced the universe up. So if it describes us and our obtaining of information from the world, then it describes how trees obtain information from the world, and it describes how electrons obtain information from the world, and how planets obtain information from the world. It doesn't matter. It's any system. So it's not just scale independent, but it's independent of everything else as well. So if one thinks about our experiences, which I do, as the outcomes of our observation, our observing actions on the world, then we have a ready-made theory for how that works. It's quantum information theory, and it applies to everything. So I think that's at least a good starting point for saying what's true of my experience is true of experience in general. And hence a good starting point for thinking, okay, well, you certainly see biological systems at all scales exchanging information. And we certainly see that information exchange affecting behavior in very important ways. And we see biological systems at all scales having experiences that, or having observations, shall we say, that they like and they don't like, that they approach to get more of and run away from to get less of, even in plants, certainly in bacteria. So why not regard this as experience? I think it's perfectly reasonable to regard it as experience.
Yeah.
And if you're willing to go to the molecular scale, then you might as well go to arbitrary scales.
Yeah. And the consequence of this are baffling.
Yes.
Have you seen any change in your personal beliefs or the way you live because of these conclusions?
Well, I've probably always had a fairly panpsychist outlook. I would say I've probably become a nicer person in the last 10 years since I started meditating. But I don't have a good answer to that question, actually.